Magic School Bus!
You've probably seen this intro before, with Miss Frizzle taking the magic school bus anywhere from outer space to inside the human body. I always wondered if there was a real bus that could let me travel inside a cell. If you think about it, we always see biology as static images, like dissected brains or MRIs. But life isn't static. Atoms are constantly moving in ways that shape every biological process. But what if I told you we have something like the magic school bus? Something that lets us see life at the atomic scale in real time. It's called molecular dynamics simulations, or MD simulations. Instead of shrinking people, we use computer simulations to watch the motion unfold. MD begins with a simple idea. If we know the positions and forces of atoms in a system, then classical physics can predict where those atoms will move next. To start an MD simulation, you need a structure. This usually comes from X-ray crystallography or a predicted model. Simulations are run using software such as GROMACS. Here, you place the protein in a simulation box and fill the box with water and ions. This mimics the conditions found in the cell. Here's an example from my research on GSK3-beta, a protein linked to bipolar disorder. I've placed GSK3-beta with lithium, which is the little green spheres. Here, I'm trying to see how lithium interacts with this protein so I can figure out why it actually treats bipolar disorder. Once the system is built, the force field takes over. A force field is a collection of mathematical functions that calculate the potential energy from bonds, electrical charges, van der Waals interactions, and more. The force field calculates each atom's position, velocity, and acceleration, and it does so frame by frame, kind of like a video, except each frame is only a femtosecond apart. That's 1/4 of a second. We then let the system relax. This minimizes the potential energy and stabilizes pressure and temperature, which avoids crashing the system with unrealistic forces. That tends to, in very scientific terms, make things go boom. After things have settled, it's time to run the actual simulation. We run the simulation for long enough for meaningful results, usually a few hundred nanoseconds. Here's the final example from my bipolar disorder system. You can see how the protein shifts in real time, and lithium moves to interact with certain parts of the protein. We finally run quantitative analysis on things like energy and distance to confirm interactions and understand lithium's mechanism of action. Now, MD as we know it is only about 30 years old, but it's already revolutionizing science. We happened to get lucky in the 1950s with lithium being effective for bipolar disorder. With MD, instead of guessing, we can watch molecular motions, helping explain why a drug binds, how a mutation disrupts function, or how a protein transitions between states. This is how we discovered GSK3-beta is relevant to bipolar disorder. Moreover, MD saves time and resources, helping accelerate progress. For example, want to test mutations of a protein? You could spend years and thousands of dollars in the lab, or you could run a month of simulations to narrow 300 mutations to 3, then experimentally confirm results. Because of this efficacy, MD simulations are now widely used in drug discovery and precision medicine. MD became the magic school bus for me, showing chemistry and biology in motion. Once you can see the motion, you can start to predict and design molecules that behave the way you want, shaping the future of health solutions.